All right, here's a quick video tutorial, I guess, where I'm trying to convince you of two rules that'll be really important when we're starting to learn shortcuts for how we're taking derivatives. And what those rules are is this first one that says anytime you're taking the derivative of the sum of two functions, you can just add up, take the sum of the two derivatives. Kind of seems like it should work, but really we're just learning derivatives. There's no reason for us to assume that this does work. I told you to assume it does work and do your homework that way. But I felt kind of guilty doing so I wanted to make sure I made a video to kind of talk you through why this is true, why we can do that little shortcut. Why, when we're asked to find the derivative of something like x to the 10th power plus x to the 5th power, all we have to do is say, well, I know the derivative of x to the 10th power, and I know the derivative of x to the 5th power, and so if I add those two things up, I get my answer. But why can we do that? Why can we go from here to here? Well, it's this rule. And I'm going to try to convince you that this rule is true by working on an example. We could prove it for general function f and g, but I think you might get more out of it if I prove this is true just for one specific example. Maybe for this example right here. Why not? I'll prove it's true with this example. And then I'll leave it up to you to see that there's nothing special about x to the 10th power. That could be any function f. And there's nothing special about x to the 5th power. It could be any function that we're calling g. So, okay, the way we're going to do this is first I want you to recall from 2.6. Recall from 2.6 that if we're going to use the definition of the derivative to find, how about use definition of the derivative to find f prime of a when f of x is equal to x to the 10th power. We didn't do this specific example in 2.6, but if you were to do it, you'd say, well, that's the limit as x approaches a of f of x minus f of a divided by x minus a. I'm not going to actually figure out what this is. I just want you to remember that this is how you set it up. And similarly, if g of x is x to the 5th, the way you would set that up is you'd say, oh, same idea. It's the limit as x approaches a of x to the 5th minus a to the 5th over x minus a. So what I want you to do is just remember that this was the setup for these two. Because if you remember that that was the setup, then what we can do is try to, we now use the definition of the derivative to find, since I've already used the letters f and g, maybe I'll say h prime of a, when h of x is equal to this original question, x to the 10th plus x to the 5th. And I'm not going to use the definition of the derivative the whole way. What I'm going to do is I'm going to kind of set things up, move a bunch of pieces around, and get to things that look like this. And we'll be like, wait a minute, I already know this is the derivative of this thing, and this is the derivative of this thing. So if I could get my answer to be this thing plus this thing, I'd know that this rule is true. So what I've done is I've kind of already worked out the left-hand side, or at least the setup for it up above, the right-hand side. Now I'm going to work out the left-hand side. So okay, here's our function. We want to use the definition of the derivative. It says it's the limit as x approaches a of f of x. So in this case, h of x, x to the 10th plus x to the 5th, minus f of a, or in our case, h of a, so minus a to the 10th plus a to the 5th. And that's all over x minus a. And you're like, yeah, that doesn't help me. Like, what can I do there? Well, we could use some algebra and sort of reorder things. X to the 10th minus a to the 10th, I could regroup things. I got an x to the 5th in there, and I got a negative a to the 5th. Just change the order around up in the top. And actually, I can do one more. can say I have something plus something else divided by x minus a. So I can really think about that as two different fractions that both have x minus a as their denominator, but the numerators are x to the 10th minus a to the 10th and x to the 5th minus a to the 5th. So what I just did there, maybe it's easier to see in reverse. If you started out with this thing, you'd be like, oh, I have a common denominator, so sure, I can add these two fractions together. You just write the denominator one time and you add what's up in the numerators. That's how you add fractions. So that would explain how you get from here to here. You can get from here to here. You can get from there to there too. One more step. You might already be able to kind of see the punchline, but one last thing. If you think back to when we learned our limit laws told us that anytime you were asked to take the limit of something plus something, you could rewrite that as the limit of the first thing plus the limit of the second thing. I think this was our very first limit law. Why is that important? Why have I done so much algebra to rewrite this thing like this? Well, look what I have right here. This is exactly this. And this is exactly this. And if you remember what these two things were, this was the setup. This was equal to the derivative, using the definition of the derivative, of x to the 10th. And this was the derivative, using the definition of the derivative of x to the 5th. These things gave me the derivatives. So what I'm saying here is I started out by trying to figure out what is the derivative of x to the 10th plus x to the 5th. And what I did was a bunch of algebra and eventually ended up with the derivative of x to the 10th plus the derivative of x to the 5th. I haven't actually figured out what those things are, but I proved that this is equal to this. And why that's really important is because there was nothing special about x to the 10th and x to the 5th. You could put any functions there. It doesn't matter what two functions you're adding up. You'll get kind of the x versions of them here, the a versions of them here. You can group things together, and what you'll end up with is the derivative of the first thing and the derivative of the second thing. So if you can kind of see that there's nothing special about those two functions that I chose, you can sort of see where this rule comes from. And so what I'm going to now do is something very similar, except show that this rule is true. And so what I'll need is another function. Remember, I can call it g of x. Let's see, let me set it up just like I did up here. What I want to do is show you that the derivative of 7 x to the 10th, sure, is just equal to 7 times the derivative of x to the 10th. I want to show you that when you encounter something like this where it's a number times a function, it doesn't have to be x to the 10th, it doesn't have to be the number 7. It can be any number, which I'll let c represent, and any function f here. When you encounter this situation, you can ignore the number, pull that out in front, and just multiply by the derivative of the function. And the reason you can do that is, well, let's see what happens if we were going to try to use the definition of the derivative. First, let's, yeah, why not? I'll color code things. Recall from 2.6 that we, actually I think I have everything that I need up above here. So everything is already up in this box. So I'm not even going to do that. I'm going to stay in blue down here and finish up this problem. Okay, so what I'm going to do is let's use the maybe difference quotient this time. No, I'm going to stick with definition of the derivative. I'm going to leave it up to you to do these with the difference quotient if you want. It's the exact same if you use this formula or this formula. But I'm going to stick with the definition of the derivative so I can reuse the work that I used up here. Make this video a little bit shorter. All right, let's use the definition of the derivative to find h again. Sure, kind of running out of letters. H prime of a when h of a is equal to 7x to the 10th. So let's use our definition of the derivative formula and figure out this thing right here. Well, what we would do is we'd say it's the limit as x approaches a of f of x, h of x in this case, h of x is 7x to the 10th, minus f of a, h of a in our case, 7a to the 10th, divided by x minus a. Well, note that I have a 7 in each of these terms up top. So really what this is it's the limit as x approaches a of the number 7 times x to the 10th minus x minus a to the 10th over x minus a. We had a limit law that said anytime you're taking the limit of something times something, you can just rewrite that as the limit of the first thing times the limit of the second thing. That's not a rule that holds true with derivatives. The derivative of a product of two things is not the product of their derivatives. However, the limit of the product of two things is the product of those two limits. So this is another limit law. And then lastly, we also learned when we were dealing with limit laws that the limit as x approaches a of 7, of a number like that, is just that number 7. There are no x's here. Change the x into whatever the hell you want. It's just a number 7. There's no x's that are changing. This is just 7 times the limit as x approaches a of x to the 10th minus a to the 10th over x minus a. Might seem like I'm just pushing numbers around, but I've actually gotten exactly what I want. Because what I want you to see here at the very end is what I now have is 7 times this thing that I'm circling right here. You might recognize it from above. It's exactly this, which is the derivative of this function, the derivative of x to the 10th. All right, this is exactly what I was trying to show. I wanted to end up with 7 times the derivative of x to the 10th when I was looking for the derivative of 7x to the 10th. So what we did is say, well, I don't know the derivative of 7x to the 10th. Maybe you do, but pretend you don't. If you don't, use the definition of the derivative. You set it up this way. If you do a bunch of algebra, not actually trying to find the answer, but just rewriting it, you'll eventually can get it rewritten like this. And the advantage of rewriting it like this is it's now 7 times the derivative of x to the 10th. What you would get if you were trying to find the derivative of x to the 10th using the definition of the derivative would be this thing right here. So what we've just done is proven this rule in the case where c is 7 and f is x to the 10th. But there's nothing special about x to the 10th and nothing special about 7. Imagine this is any function you want in any number. This is the number 11, and this is the function square root of x. This is an 11. This is an 11. This is square root of x. This is square root of 8. A. Factor out the 11. That'll end up right here. And then what you'll end up with here is square root of x minus square root of a over x minus a. Oh, that's exactly the derivative of the square root of x. It doesn't matter at all what function this is, just like it didn't matter above what function these are. So really these rules, I just showed them with an example because I thought it might get confusing if I just proved them generally speaking. But if you can just kind of see that there's nothing special about what I chose, then you can kind of see how the proof would work generally. And so maybe now you can kind of see why these rules apply, where they come from. So from now on, when you're using them, you won't be like, yeah, because he told me to memorize them. You'll be like, oh yeah, because I kind of remember those coming from the definition of the derivative. I guess I'll call that good. I'll end this video here.